cruise control example and apply some of the MATLAB tools to it so that we can both tune and verify the controller that we've designed. So to review, here's the block diagram of our cruise control example. Using tools that we've gone over in class by hand, we designed a PID controller to place the two dominant second order poles at -0.5 plus or minus 0.5 J, which should give us a settling time of about 8 seconds and 5% overshoot. Of course, that ignores other poles and zeros that might be close to the origin on the real axis. But here's the controller that we came up with. So now we're going to take that controller and the rest of our system, put it into the control system designer, do a little bit of tuning. Here's what we're going to ultimately come up with, something like this. And we'll take that, build a Simulink model, and then we can test to see how well our controller handles a disturbance, in this case the car going up a hill. So to start, let's enter all our components. So going around the circle, we have our controller, 0.215 times s plus 2.77 times s plus 1 over 20 divided by s. We've got our tau 0, the torque constant, which is 500. We've got the dynamics of the car itself, 1 over the mass, which was 1,000 times s plus 20. And our sensor dynamics, which were 1 over s squared plus 1.4 times s plus 1. So now we can put all this into the control system designer. And remember, this wants the plant, in this case our g times tau, the compensator, the controller, c, and the sensor. So we have tau times g, c, h. Alright, so now we've got this loaded up. There's a couple things that we want to notice that we can improve a little bit. First of all, our settling time is definitely longer than we wanted. We can look at this more explicitly if we add in the settling time here. So it's about 35 seconds. That is because we do have a pole, a closed loop pole close to the origin between that pole and our, from the integrator, and the zero associated with that integrator are in there. So we're going to want to fix that. If we look at our phase in the Bode plot, there's a lot of ups and downs. That generally is going to look better if we can smooth that out and have it more monotonically decreasing. And then lastly, if you look very closely at the step response, it doesn't actually seem to start at 0, and that's because we have a pure derivative in this controller. And so we can fix that by turning it into a lead controller instead of just a pure derivative component. So let's start out by making some adjustments to this 0 location to smooth out the phase. So if we take that 0, we can just pull it back until it's essentially pretty close to this other pole here. That'll ensure that we have a nice continuous slope of minus 20 dB per decade, and our phase is going to drop down. Now we did introduce some overshoot. That's okay, we'll deal with that later. Essentially we just are going to need to reduce the gain a little bit, and you can see that'll go away. And our settling time is already quite good here. Now we're still starting out at, not starting out at 0 with our step response. So let's add in a real pole that we're going to put out kind of out here. This will convert our PD controller into a lead controller. And now you can see that we are starting out at 0. There's a very sharp spike initially. You can tune sort of how sharp that is by choosing where you place this pole here. So if we bring it in a little bit, we get a nice smoother response here. It does increase our settling time a little bit, but not too bad. From here, you could adjust your gain a little bit. So if you are very careful with it, you can get your settling time down to close to 4 seconds or so, with just a tiny bit of overshoot. So this looks pretty good. Once you are happy with your controller, you can take a look at it. If you click on C here, it'll show you what that is. This is a little different than what I wrote down on the sheet, but ultimately gives a fairly similar response. So that's the control system designer for tuning. You'll want to write this down so you can use it in your Simulink block diagram. So we'll close that out. And now let's work with our Simulink model. So again, I'm going to use this final controller. It's just a little different than the other one, but close enough. So let's bring up Simulink. We'll say create a model. And we'll click on Simulation, Library Browser. Now we're going to need to collect all our components. I've put a little cheat sheet here because some of the components are hard to find. So first we'll click on Simulink, then we'll click on Sources. This is where we're going to get the inputs to our system. All the way at the bottom here, roughly, is our step. We're going to need two of these, one for the hill and one for the desired velocity. So those are our sources. We're going to need a sink, that is, we want to see the response of our system. So we're going to use the scope for that. I'll put that kind of here. And then we're going to need some zero pole gain systems, and those are going to be under continuous, and they're all the way at the bottom here. So this is going to be what we use for our controller as well as our car system and our sensor. Our sensor, we're going to need to flip this. If you right click, go to format, you can flip the block so it goes the other way. We'll connect them up in a moment here. Then we're going to need a bunch of gains. So if you go to math operations, sort of in the middle here is your gain block. We're going to need one for our torque constant. We'll need one for the hill. And I'm also going to add one for each of the step responses, just so that we can easily turn them on and off without editing the step response itself. And that should do it there. And then the last piece we'll need is we're going to need two different summing blocks, which are towards the bottom here. Or actually, sorry, they're towards the top here. We're going to need two of these. Now I'm going to give myself a little more room to organize everything. So let's enter our different systems here. So for the controller, I won't be able to see that. We double click on that. Our zeros here are going to be at -1 and -0.02. That corresponds to zeros for this controller here. And our poles are at 0 and -5. And our gain is 5. Now if you stretch this guy out far enough, you can start to see those values. There we go. Now we'll put in the dynamics of the car. So here, the numerator, there are no zeros. The poles, actually, the poles are 20 minus 20 over n. So minus 20 over 1,000, and the gain is 1. The sensor is actually going to be easier if we enter it as a transfer function rather like a polynomial rather than pole gain format, so we can use that transfer function block, which is also under continuous, and we'll flip that guy around. Alright, so the numerator is just 1, the denominator is 1, 1.41. So again, if we stretch this guy out, we can see it. Okay. Then we had our torque constant, which was 500. And we have our hill, which was minus mg, so minus 1000 times g, we'll just say that's 10. And if we stretch that out, you can see what it looks like. Okay, so now we can start to add in all of our pieces. This block here is not actually a summing block, it should be plus minus, so if we double click, we can change that there. Then this guy is going to connect up here, and our hill, just connect all these pieces, and that goes into our system. Pull this out a little bit. This is going to connect up to our sensor. This is going to connect up to that block, and then this guy connects up there. You can make it look a little nicer. And then we need to connect our scope. If we hold down Option and hover over the line, or if we go back this way, there we go. Now that's connected. So now we have our entire, we just gotta connect these guys up. Okay. Now we have our entire system plugged in to Simulink, and now we just need to set the step inputs. So what we'll do is set this guy to have a step input at time 1 to go to a final value of 0. That's the default, that's fine. And then this guy, this is the hill. Let's make this happen at a different time. We'll make that happen at time 10. And we'll set the final value to 0.15. This is in radians. 0.15 radians is about 8.5 degrees, which is the average slope of Donner Pass. So it's a reasonable step input to see what happens with the hill. So now we have everything set up here. If we click on simulation, we can now, let's edit the stop time to be, we'll make it go out to 300 seconds so we can really see what happens with the hill. And now if we click run, it'll run the simulation. It's not happy about something here. It's not happy about this block. Oh, this should be. Let's see, is that? Okay. Let's replace that 0 pole block with a transfer function block, since that's how it was defined anyway. Maybe I made a mistake. Oops. Defining that. So this is 1 over 1000s plus 20. Oh, okay, I think it's happy now. Yes, okay. So you can see here, if we look at the simulation, initially, this was our step response to go up to 1. There was a little bit of overshoot, and it started to settle, and then we started going up the hill, and then it started to accelerate to get back up to speed where it was originally at. So you can see the final steady state error is indeed 0 because we do have that integral term in there. It does take a while to get there, on the order of 200 seconds or so. So 3 minutes or so going up the hill. The thing that's fundamentally constraining that is that we have a pretty slow sensor, and also we have, kind of a heavy car that's going up the hill. But overall, this is, acceptable. We can see that our controller did ultimately do its job in rejecting that disturbance, albeit not super quickly. But overall, we should be pretty happy with this. So this is a good tool for seeing your response to the disturbance. If you want to make a nice plot, it would be better to define that transfer function and do that separately. So again, the transfer function between your hill and your output would be all of the blocks that you find in between those two. So it would be the minus mg and the g. divided by 1 over 1 plus the loop transfer function, so all of the blocks that you have in this circle. That's all for this video.